Hello, everyone. Very good morning. Okay, so we are back again after a break. Now, in the last week, we have done something interesting, and the topic was large language models, right? In the large language models, we were looking at what exactly is large language model, how does it work, and what are the components inside of that. We talked about so many things: the fine-tuning concept, the RAG concept, and the prompt concepts, few short learning, and that zero shot learning. Different things we were talking about, right? So I hope if you have gone through that, you would have understood a lot of things inside of that. I have shown those things on AI tool also. I was using a website perplexity.ai to show you how do they work whenever you try to write prompt. In the case of zero shot learning, in the case of few shot learning, how the things are changing, how the things are affecting. So we have looked at multiple practical versions of that also. And as you move forward, you will see more in-depth versions of this using those concepts. Now, today our main focus will be a concept called as BERT. Right? BERT is also very similar to the transformers and the LLM topic we were talking about as of now. So BERT is one of them. And what exactly is BERT? It's very famous topic when you talk about generative AI or large language models or transformers. It's a very famous topic, and it's a very famous tool which is also used uh, when you have to make a language model, which should be able to do question answers, which should be able to do text summarization kind of things. So this is also very famous and used in some small case. Now, so till now, the first thing we discussed was that I have taught was transformers, and we have seen that the journey of transformers started in year 2018. In 2017, a paper was written, which was "Attention is All You Need." And on the basis of that, the entire NLP industry changed, right? The entire NLP industry changed. So before this transformer concept, we were using RNNs, LSTMs, GRUs that we have seen. So out of that, these two you must we have seen what they are and how they work. So this before the 2018, these were very famous RNN, LSTM, and they were used for NLP tasks, natural language processing. But the problem was that RNN, LSTM don't have an infinite reference window. They are not able to remember the entire context of a you can say statement. If I give a paragraph which I have to summarize, or I have to do a question answer kind of thing. So they can't remember all the data which I have given it. It remembers only a very limited context. It does not have a very infinite reference window. It can't refer to the entire text while answering something, while summarizing something. They had this problem. So after that, in 2017, when the paper was written, "Attention is All You Need." So in the year 2018, that paper was implemented, that paper was converted into practical tools, and that tool became transformers. Right. So transformers was basically mentioned in that paper, "Attention is All You Need," and it was converted to its practical form so that we can use it for NLP task. So this was created. Now, when transformer was created, it was like uh, changing for the entire industry of NLP because it was able to do a lot of things which was not capable, which was not possible before. And it was able to do summarizations much properly, text generation much properly, because it has a very long, or you can say infinite reference window, as we have seen. Because of that, it can understand the context very well, right? The good things about transformer is that it can go both the ways, left to right and right to left in a text to understand what is the entire context of the text. But RNNs LSTM were unidirectional kind of thing. They go from either left to right or right to left to understand a concept. But when the transformers see a statement from left to right and right to left, they are able to understand the context much better. And they are also able to connect which word in a statement is related to which another word. They are also able to connect that. Right. So these are the things which were possible with transformers. And transformer was quite good for a lot of tasks, but there was a need for updation. There was a need for some other tool, some other language model, which can understand context more than that, which can be trained on larger data set to be able to work more properly. See, the whole context is the more data you use to train any of these tools, the better they were. These are called language models. So the more the data is given to a language model for the training purpose, the better they understand. That's the basic idea. So transformers were able to get larger training data and work with that, but that was not too large to be able to use in the real world. So after transformers were used. So after transformer, the BERT was created, right? BERT was created after transformer. This is the updated version of transformers that has been brought into the market. And when BERT was brought into the market, it was much larger than transformers, and it was able to it was trained on much larger amount of data than transformers. So it is, you can say, another version of that. You can say it's an updated version of transformers. Correct. That is the thing. So now this is what we are going to study. What exactly is BERT and how it is different from, or how it is updated on top of transformers. That is what we will talk. So at the end of 2018, researchers at Google AI Language open sourced a new technique called as BERT. This is a short form for bidirectional encoder representation from transformers. Right. So this was the name BERT, and it was created. It was a major breakthrough. As I said, it was very game changing for the entire NLP industry because of its capabilities as compared to the previous existing tools. Before this, before the BERT, there were transformers and RNNs and LSTMs. So when you compare BERT with the previous tools which existed, it was much powerful than that, and it changed the entire industry after that point when this BERT was created. So we are now going to talk about why was BERT needed, what is the core idea behind that, how does it work, and when can we use it. The fine-tuning part of that will be covered in the upcoming sessions, but for now we will be talking about the implementation of and the core idea behind the BERT. Now, so why BERT was needed? The main thing we need to understand the context was why people were searching even for this BERT when they had transformers, when they were LSTM RNNs, why there was a need for the BERT. Let's take a look. So one of the biggest challenges in NLP is the lack of enough training data, right? Lack of enough training data. But you see, by the year 2018, in the real world around us, we see there is a huge amount of data. So overall, there is an enormous amount of text data available, right? Overall, there is enormous amounts of text data available. But if we want to create task-specific data sets, But if we want to create task-specific data set, we need to split the pile into very many diverse fields. So suppose whatever data is available on the internet, the entire data, that is related to multiple domains. Some data is related to finance, some data is related to sports, some data is related to literature, some data is related to mathematics. So whatever statements, whatever paragraphs, whatever articles, documents, PDFs, whatever data is there on the internet related to languages, they are related to multiple domains. Correct. And if you look at these multiple domains, so they overall the data is very large. But if you take a look at a particular domain data out of this entire data, that is not very large, right? That is not very large. So overall, there is an enormous amount of text data available. But if we want to create task-specific data sets, we need to split that file into many diverse fields. We need to split our main data into diverse fields. And when we do this, we end up with only a few thousand or a few 100,000 human labeled training examples. So when we break it down into multiple of the domains, when I divide the data into multiple domains, then we have very less amount of data for a particular domain. Domain wise, we have very less data. So unfortunately, in order to perform well, deep learning based NLP models require much larger amount of data. So deep learning has this thing that when you give it a very large amount of data, then it works quite well. But if it has a less amount of data, then you are not actually using the real power of the those neural networks. So this was the problem. Now, how to solve this problem? Right? Yes, the more we go into the domain, the lesser the data becomes. That is the basic idea. So this was the problem, that we have very capable tools like deep neural networks, RNNs, LSTMs. We have a very capable networks. We have transformers that was also very capable. But the problem was that if I have to create anything which should be able to understand those specific things, like they should, those language models should be able to answer finance questions very well, or they should be able to answer medical related questions very well. So they need to be trained on these specific data so that they can work well. They can be usable in the real world for a particular task. That was the problem now. So until you give the deep learning NLP based models, until you give it a much larger amount of data, it is not very good. It is not very usable in the real world. So they see major improvements when trained on millions or billions of training example, then they work very well. So you need to give millions of statements, billions of statements, paragraphs, then they are able to understand the pattern very well, like how is a statement constructed, how is a grammar understood, how is a inherent meaning of the statement understood. That is what is happening when millions and billions of the statements are given as a training data. But we did not have that much amount of that to give to these models. We were having around few 100,000 statements which were usable from the entire internet. So like 100,000, 200,000, 500,000. We were having that much amount of data which was usable for the training purpose. Now, to help bridge this gap in the data, in this training, in this data, in the capability of these models, researchers have developed various techniques for training general purpose language representation model using the enormous pile of unannotated text on the web. This is called pre-training. So to overcome this situation, they saw that on the internet, there is a huge amount of data available, because you see, the data on the internet is being created since the time internet was created. So from around 1995, the concept of internet started, and slowly people started adapting that. So overall, from 1995 to 2018, we have good enough amount of data, right? We have good enough amount of data available on the internet. But the problem is, a lot of that data is not ready for the training purpose. We can't use that for training purpose because it is not, uh, you can say, labeled. What type of statement that is, what type of document that is, it is not labeled. Is it a finance document, or is it a medical related document? Is it a sport related document? So what type of document that is, most of that document is not labeled. That was the problem. So there was a lot of data, but the usable kind of data was less. And when we break that usable data into domains, it becomes even less. Correct? It becomes even less. So that is the problem, that overall, yes, understand this. Overall, there was a lot of data. If I talk about statements, paragraphs, documents, and PDF files and all of that, wherever we have language kind of things, that data is a lot on the internet. But usable data is very less. In many of the documents, in many of the PDFs, it was seen, if you download them, if you use them, there is no mention of what type of document it is. Is it related to e-commerce? Is it related to sports science? Is it related to medical? It was not mentioned in that, right? So because of overall theme not mentioned, overall labeling not done on that, so when you give it to your transformers or any model, language model, they won't be able to understand, okay, I'm learning this document, but what is this document all about? I don't know that. So that learning is not going to help us. So a lot of data is not labeled. And if you break down that data into domain wise, that becomes even less, the domain wise data. Right. So usable domain wise data was found to be very less. So to bridge this gap, to say that we already have a lot of data, but the problem is happening by using transformers and RNNs and LSTMs. The main problem is happening that the lot of data is not labeled. What is that data all about? It is not labeled. So the transformers and all of them, they work very well. They are able to understand the document if the labeling is there. So they can understand that, okay, I'm learning this document and this document is about this particular topic. So this was not there. To overcome this situation, that even if I have a unlabeled data, right? Even if we have unlabeled data, which is this unannotated text on the web. So if it is not mentioned what kind of data it is, what kind of paragraph it is, what kind of document it is, even if it is not mentioned, we have to create a model, we have to create a language model, which should be able to automatically understand the theme of the data, right? So we were having this need that it should be able to understand automatically the overall theme of the data. We should not be needing to give the theme ourselves. We have to create such a model, such a language model, which can go to a document. If the labeling is not done, it should be able to read the document from left to right, right to left. The entire document it should be able to read and find out the theme itself. So this particular thing is called pre-training. Pre-training is a process. Pre-training is a process where we take a data, right? We take a data and we give that data to, yes, we give the data to a language model. Language model means any of these language models, like Transformer is a language model or BERT is a language model overall. So we give a data to the language model, and if the data is not annotated, if it is not labeled, then also our language model should be able to learn the overall idea about that data. So when it has an overall idea about the data, it will able to understand the pattern. It will be able to find out the pattern present in the data itself. Right. Now, when these data, the labeled, unlabeled, all of the data, when it was given to the language model, that is what we called as pre-training. Now, these general purpose pre-trained models can then be fine-tuned. Once you have done this, once you have created a pre-trained model, so pre-trained model is like that student. Think of the pre-trained model is like that student who has been taught everything from class 1 to class 12. Right? During class 1 to class 12, we see that in schools we are taught a lot of topics: mathematics, science, Hindi, English, social studies, uh, mathematics. Multiple things are taught to us, but we are not becoming expert in one particular thing during the school time, right? So think of pre-training as a student who is having an overall idea about the world around us. What does mathematics do? What is the overall use of mathematics? What is the use of science overall? What are the things inside of science? What are the things inside of social studies? So only the thing is, this language model is able to understand. If you give it a document, if you don't tell it that it is science related, it will be able to understand that it is science related by doing a overall look at that, by doing a overall analysis at that. It will be able to understand, in the case of unlabeled document also, that what it is all about. Is it about medical? Is it about specifically, you can say, heart diseases? What kind of medical thing it is? It will be able to capture the overall theme of that. So think of a student who is much smarter, who is taught something, and when the student looks at something new, he is able to understand what is that all about, what is that topic all about. So think of this pre-trained model, whatever, whenever we see pre-training, think of that pre-trained model, language model, as someone who has been trained on general data around the world. But this pre-trained model, whatever we use, whatever language model we have, they are overall good in the way generalized things work. So if you ask it normal questions like who is the president of this country, or what is this concept, or what is that concept, it will be able to answer it very well. But the problem is with these pre-trained model that they are not good for a particular domain. They are not very advanced for one particular domain, for a specific task. They are not ready for that. So these general purpose pre-trained model can then be fine-tuned on smaller task specific data set. When working with problem like question answering, sentiment analysis, when we have to do more, you can say, a fine-tuned task, that I have to use it only for the medical and it should be giving us very correct answers. So in that case, we can fine tune it on those task specific data set later. But let's first create a student who is pre-trained first. Now the overall idea is, so if there is a student, the overall idea what they were trying to or what they were thinking is that, let's say there is a student who is taught from 1 to 12. This student is taught various topics, right? Various topics, mathematics also, science also, Hindi, English, literature, all of that. This student is taught various topics during their training phase. So class 1 to 12 is their training phase. They are trying to understand the world. How does it work? But think of another student. If you try to teach this student only finance from the start, right? From class 1 to 12, when the student started learning actual things, so you teach only finance from the start. So it is, the overall idea is that this student will not be very good, will not be as good as this student who is first taught various topics, then taught that specialized in their college, then they are taught the specialized topic. But from 1 to 12, they are taught various topics, generalized topics in the real world. So this student will be able to understand much better because this student is learning multiple domains and this student is able to make connection between multiple domains. So the learning capability of the student will be far better than this student who was only taught one thing from the start. Now we can say that this student will become much better in finance, but it is seen that overall, if this student is there who has been taught various things, if they have overall idea about the world, if they are taught about the specialized topic later, they can become much better. They can connect finance with other domains to be able to have a very large understanding. So that is what we are trying to do in language model overall in the real world also. First, do the pre-training in which we take a student or we take a language model and we teach it all the things, whatever is there in the internet, teach everything it. But at that point, it is only generalized. It is not very ready for specific tasks. So then we do what? Then we do the fine tuning. We give it a particular data set and then we fine tune it on that. And then it becomes better for the specialized task. So it is having best of both, the generalized knowledge also and the specialized knowledge also. It has both. So it becomes much more capable, much more powerful than this kind of student, the first. Right? So I think you're getting the overall idea. What was the limitation and what we are trying to do, how they were thinking before creating the bird. So how they came up to the point that they thought that a new language model is needed. And what kind of language model is needed? The language model should be able to do these things. The limitations they should be able to overcome. So this particular approach of first pre-training and then fine-tuning that, this approach results in great accuracy improvements compared to training the data on smaller specific tasks from scratch. Right? I was just explaining this student and this student, right? So the thing is that when we talk about these two students, it is seen that this one, which is first pre-trained on large data, then fine-tuned, this student works much better. There is a great accuracy improvement in this student or this language model as compared to this language model, which is only taught one thing, specific data from the start. Now, BERT is a recent addition to these techniques of NLP for pre-training. It caused a stir in deep learning community. It was very shocking, or it was very exciting for the NLP community to have this kind of thing, because before the BERT was released, before the BERT was launched into the real world, people have not thought that this would also be possible. Going forward, we would be able to do these kind of things. We would be able to use a AI related tool in the real world to answer questions so properly, so accurately. They have not even thought about that. But because of this capability of pre-training and fine-tuning, it was seen that it was able to do such things that after some time, after some updations of the first version of the BERT, we can do a lot of things. So they started to vision that at that point. So this is where the BERT vision came into the picture. This is the point. Now let's see what is the core idea behind that. Now, whatever we talk about, transformers, BERT, GPTs, all of that, they are language model. And we have seen what language model is. So what is language modeling really about? Which problems are language model trying to solve? Whenever we talk about a language model, that's a way to represent data. That's a way to represent information so that we can use it to in the real world for question answering, sentiment analysis, summarization. We can use that. It creates a model. So which problems are language models trying to solve? Basically, their task is to fill in the blanks based upon the context. Overall, if you see, their task is to fill in the blank. Like suppose you are asking a question, who is the president of United States? So the answer that it is giving you, it is also overall kind of a filling in the blank, that you have written a statement, and after that, what should be there? You are asking for that. So kind of you're filling the blanks. So the main task, what it was used for, the woman went on to the store and bought a pair of shoes. This is one example of filling in the blanks. And another version of filling in the blanks, also you can say that question answers us is same as that. You have written one part of the statement. Now you are looking for what is further. The answer which this is going to give is the further thing you are filling in there. Right? Now, when you have asked who is the president of the United States, so it has given us the answer, let's say. So on the basis of this answer, you can ask further questions. Okay, from where does he belong? What is his religion? Or can you tell more about his family? Can you tell more about his education? You can ask further questions on top of that. So you're further completing the things, you're further generating the data more and more and more. So you are kind of filling in the blanks. Overall, it is called that you're filling in the blanks further and further and further. And that is how we are generating the answers. So one concept of filling in the blanks is this, and one concept is generating the answers. Yes. So in this case, you see, when you have this kind of statement, so your language model will not be able to find out the answer directly. It will find out multiple answers which are usable for this place. Then it assigns a probability that which answer is good. Should I use the cart here? If I say woman went to the store and bought a cart of shoes or a pair of shoes. So it will kind of assign a probability. And on what basis it will assign the probability? On the basis of the training data. See, overall performance of the language model in the real world depends upon the training data. The most important aspect is the training data. Everything, training data is the most important thing. If your training data is bad, then whatever results you're going to get in the real world, whatever answers you're going to get, that will also be bad. We have seen in the last case that the authenticity of the data is very important. If suppose someone has modified the data according to their thinking, according to their opinions, ideology, so we will also be getting answers according to that. Whatever way they have created the data, they have modified the data. So the data must be as such, the training data must be as such, using which we can get the correct and neutral answers. It should not be based upon someone's opinion. It should be neutral. So in the training data, it must have seen that cart was present at this place in this context 20% of the time, and pair word was present here 80% of the time. So from that knowledge, from the training data knowledge, it will be able to understand which one seems to be better, right? As compared to both of them, which one is better, which one is was used most in this context. If the word pair is used most in this context, then it will be filling it with the word pair. But it will be searching for multiple answers and then fill it with the most probable that can be there, according to the training data that it has seen. Now, that is what the language models are trying to do overall, kind of filling the answers. In a pre-BERT world, we are saying that in a pre-BERT world, I'll share this link to you if you want to follow with me. Just a minute. Yes. See, so in a pre-BERT world, a language model would have looked at this text sequence during the training from either left to right or combined left to right and right to left. Right. So before BERT, in the pre-BERT, when BERT was not launched, any language, when you talk about transformers or RNNs or LSTMs, those things, they would have looked at the text sentence during this training, either from left to right by going through left to right, or they would have looked at right to left, or a combination of both. First, go from left to right and then right to left. Now, this one directional approach works well for generating sentences. Now, this one directional kind of thing, most of the things were this one direction. Either you look at a statement from left to right or you look at a statement from right to left. Now, this one directional approach works well for generating sentences. Mainly the thing which was happening was left to right or right to left. The combined part was very less. Very few language models were there before BERT, which can do both left to right and right to left. Only transformer was there, which can look at any statement from left to right also, right to left also. Apart from that, if you talk about RNNs, LSTMs, they only work in a unidirectional method. So many of the language models before BERT were working on unidirectional approach, one directional approach. They work very well for generating next word. For generating sentences, we can predict the next word, append that to the sequence, then predict the next word to next word until we have a complete sentence. right? So suppose it is said that India is great because, suppose we have written this statement, India is great because, now it has to fill the further things. So now it is looking at the statement from left to right, like that India is great because, now it will generate the next possible word. And then it will look at the statement again, India is great because this. Then on the basis of this new predicted word, it will predict the next word, then next word, the next word, the next word. So for predicting any next word, the transformers, RNNs, LSTMs, all of them, they see the previous, all the words, all the tokens, and on the basis of that, they decide what is the next probable word, the most probable word. And that is how they work. But sometimes one directional approach is not very, you can say, complete. It is not sufficient to understand something to do the text generation. Because if you go in a unidirection method, you can't understand the entire context of that. We'll see an example of it. But that was happening most of the time. The things were going unidirectional. Now enters BERT. The BERT is a language model which is bidirectionally trained. So this is its innovation, technical innovation, that BERT is bidirectionally trained. Whenever you give it a training data to understand something, so when it is learning how a sentence is formed from the training data, when it is looking at those documents or PDFs from the internet and multiple articles, so it is not looking at a particular statement or a paragraph from one direction. Like after this word comes. After this word comes. It is not learning like that. It is learning in both the directions. At the same time, it is going from left to right also and right to left also at the same time. And in this way, it can have a deeper sense of language context and flow compared to single directional language model. So when you're looking at something from both the side, you can understand things better. Like suppose there is a word bank. I'll show you an example. So suppose there is a word bank which is used. So now this bank is referring to the financial institution, the bank where we go and open an account, or is it talking about the riverside? The riverside is also called as a bank. So is it referring to that bank, which is financial institution, or is it referring to riverside? That will be understood much better when the bird is looking, or when any language model is looking at the statement from two directions. Because when the word bank is used, somewhere later, there must have been a word river also, or some sort of water body must have been talked about. So your bird will be able to connect, okay, river is written, bank is written. So this bank is referring to that in the context of the river, not the financial institution. So bird will be able to relate that much better as compared to unidirectional things, unidirectional language models, because it is looking at a statement from both the side at the same time. Now, instead of predicting the next word in a sequence, BERT make use of a novel technique called as masked language model. Right. So we are going to understand now how BERT is able to do these things, how BERT is able to perform better than the previous language model. First thing is that it is bidirectionally trained. Any statement it is given, it learns that from two directions at the same time to be able to understand the context much faster. And how does it do that? The first thing it uses, the first technique it uses inside of that is called masked language model, masked LM, which is it randomly masks words in a sentence, then it tries to predict that. So whenever a training data is given to it, whenever the training data is given to the BERT, what it does for learning the pattern, what it does to understand what is the next probable word, because by just looking at the statement, it won't be able to remember, or maybe it won't be able to understand the context. So what it does to learn the context more properly, it takes these training data, randomly any statement, and what it does, if suppose this statement is written, so what it will do the masking of some words. Let's say it is masking this word. Masking means it will hide these words. So there will be a statement and it will hide that. Then it will try to predict, okay, what should be here? Or if I have the word non-directional and if I hide this word approach. So what should come after non-directional? This is called mask LM. It takes the training data where the things are mentioned, but it will randomly hide something from the statements. There are multiple statements, millions of statements are there in many documents. It will take any statement, hide something in that, and then if it try to predict, if it is able to predict something, then it will compare. Have I predicted it correct? Or if I have predicted something, was it close to what should have been predicted, or am I very wrong? So if it is very far away from the actual, very different from the actual, then it will try to change its approach of learning. Okay, it will adapt according to that. No, no, my loss is very high. So I need to, uh, whatever I'm predicting, whatever I'm trying to find out, it should be closer to this particular context. I need to understand this statement in this context. It will learn itself. So by masking multiple of these statements, it will be able to understand the context very well. So during the training phase, it is doing these kind of things. So then in the real world, if you give this kind of statement, it is ready for predicting the further words. If you ask a question, what should be the answer of that? It will be able to answer that more properly because it was training itself on those kind of situations. So it says that BERT uses a technique called as mask LM, which is during the training phase, it randomly marks the word in the statement and then it tries to predict it. Masking means the model looks in both directions and it uses the full context of the statement, both left and right surrounding, in order to predict the mask word. Now, the good thing about the BERT is that it does not go only in this direction to predict this word. The RNNs and LSTMs mainly, what they do, they will go in one direction from here to here to be able to predict the next word. They won't be looking at the further words to predict this mask word. But what BERT can do, BERT can go from this side also and BERT can go from this side also. And by going from both the side, it will be able to understand that context much better. What should be the word predicted here? What should be the word present here? It will be able to understand the grammar and the context and the sentence formation more properly. Now, unlike the previous language models, it takes both the previous and the next tokens into the account at the same time. That is very important. So it is looking at the previous word, or you can say previous words and the further words at the same time. So it is trying to connect this and this both together at the same time. And that is very important. This is the word which is very, very important, which was not done before. So when it uses or when it connects that at the same time, then it is able to uh, find out this word approach very properly. Now, so you must be thinking that I have taught about the transformers also. And in the transformers also, we have seen something that if I have written a statement, so transformer also connect to the previous words, right? Powerful, approach, or what word is related to powerful, what word is related to bidirectional, whatever is that. Transformer was able to also do that, right? But how the BERT is different from that? BERT is also the same thing which the transformer was, but the BERT is doing that on a larger scale, right? The main difference between the BERT and the transformer is that BERT does this on a larger scale. So in the transformer, we were saying that we have some encoders. We have one part which is encoder, and then we have decoders. Right? There are two sections of the transformer. When we have seen the architecture of the transformer, there were two things. Input is given, whatever input statement is there, it is given to a box which has encoders. And it has multiple encoders inside of that. Not one encoder, but multiple encoders are there, which understand the meaning, context, syntax, different things that different encoders understand. So if you have visited that video, if you have watched that video once again, you may be able to remember that. I have told you a number. How many encoders are there in that box? The first part of the box where we give the input and it is encoded, it is converted into those vectors which can be given to decoder to predict something or answer something. So there are basically six encoders connected together, one after the another. There are six encoders together. And what these six encoders are doing, all of them are trying to understand different version of this statement, different meaning of the statement. One encoder is trying to understand the grammar. One encoder is trying to understand the language, which language is this in. Then another encoder is trying to understand the syntax of it, that which word is written how and which word comes after which word. So there are total six encoders connected together sequentially one after the other, and they all try to understand different themes from inside of a given input statement. But is what? But is just more number of these encoders. So whenever you take an input and you give this input to this box, which has encoders, BERT has just more encoder. It will have 12 encoders or 24 encoders. There are two versions of BERT. One has 12 encoder, 24 encoder. That using that, it is able to understand more in-depth context of a given statement, more themes or more things about a statement by using more number of encoders. So transformer, whatever it was doing, overall BERT is also doing the same thing, just it is larger than the transformer. Think of a updated version of transformer which has more capabilities to understand what a statement is trying to say, what context is overall. It's a larger version of the transformer. Correct. So that is the thing. The transformers also are able to understand the meaning same time, that if I have this word approach, transformer will also go like this and like this. But BERT does that with more number of encoders. So it is little bit more powerful than transformers. That is the whole idea overall. But apart from transformer, if you look at RNN, LSTM, they only go unidirectional. RNN, LSTM can only go unidirectional, either left to right or right to left. That is the idea. So the BERT is basically a next version of transformers. That is overall, you have to understand. BERT is overall the next version of transformer. That is a transformer when made bigger, then we get BERT. That is what happened. Now, so till this point, are you all understanding what we are trying to see? Are you getting what I'm telling? See, you won't be able to remember all the things. I'm not saying that you remember everything because I have discussed so many things. But when you go through this document, you will be able to understand then very properly what every word is saying, what every statement here is explaining. That you will be able to understand. But understand overall what I'm trying to say, what are the words I'm using. But overall, after once you go through this video, then you would be more clear about that. Yes, overall, that is a kill. That is the idea. Correct. Perfect. And what is BERT? It is a language model, right? Language model. Transformer is also a language model and BERT is also a language model. Then what is large language model? Large language model is nothing but when you take a language model and give it too much data, right? Whenever you take a language model and when you train a language model on too much data means you have, let's say, 100 billion statements. You take a lot of documents from the internet and you give 100 billion statements to the language model. It is a very large amount of data. 100 billion is a lot. If you see, 100 billion can't be counted in our lifetime. If I have to count one by one every number, that is too much. 100 billion is too much. So whenever a large amount of data is given to a language model for it to learn something, that is when it is called large language model. So large language model is nothing but a language model which is trained on huge amount of data. Huge means very, very huge. That is the overall idea. There is nothing separate between them. So that's just a name to identify that this is trained on large amount of data. And when we say LM, it is trained on millions of statements, we can say. It is trained on little less number of statements. Now, so why is this non-directional approach so powerful? So non-directional means bi-directional. So they are saying that we can call this bi-directional when we go from left to right and right to left at the same time. At the same time, when we go, we can call this non-directional also. We can call it bi-directional also, or we can call it non-directional because it is going in both the direction. So sometimes you will see this word being used, sometimes bi-directional, both them mean the same thing. And one directional will be called as unidirectional, but bi-directional can be called bi and non-directional. Now let's understand this part. This part is little bit more technical and you will see examples now. So pre-trained language representations can either be context-free or context-based. Now, what do we mean by context-free or context-based? So context-based, any of the language representation, any of the language model we are talking about, they can be of two types, either context-free or context-based. Two things can work. Now, what they are? Context-based representations can be unidirectional and bidirectional. If I talk about context-based, they can be unidirectional also, and they can be bidirectional also. Both. Some model can be unidirectional, some model can be bidirectional. And context-free models like word2vec generate a single word embedding representation for each word in the vocabulary. What is context-free saying? Context-free is saying that whenever I have to look at a word and whatever I have to do with something, I don't care about the surrounding words. What do we mean by context free? Context free means that if something has to be done on a particular word, such as embedding has to be done of a single word, I don't care about what is the word before that and what is the word after that. Right? I don't care about that. I take a word and then do the encoding of that in a certain way. For example, in the context free, if suppose the word bank is given, so the word bank would have the same context free representation in bank account also and the bank of the river also. Because context free language models are not looking at what is around that. They are just looking at this word. So suppose the bank is with the bank account or bank of the river. In both the cases, the word bank will be represented by same word embedding in the context free cases, right? So pre-trained language trans representations can be context free or context based. Whenever we are representing something as a language representation, so it can be context free, context based. Context free says that whenever I take a word, if suppose I have to do word embedding, suppose as an example, I don't look at the surrounding. That is why the word embedding for this and this will be same, which is not very good, which is not very accurate, because both of those things mean the different thing in the overall context. On the other hand, context based means context based models generate a representation of each word that is based on the other words in the sequence. So context based approaches try to look at the other words also before doing something on a particular word. They don't just look at one word as an independent word. They try to connect it with the surrounding words and then tell what is that in the context of the entire surrounding. For example, in the sentence, I accessed the bank account. Right? I accessed the bank account. A unidirectional contextual model would represent the bank on the basis of I accessed, but not account. So what will happen in context-free unidirectional approach? What you can say here is, it will only look at the word from one side, or you can say independent. It is not looking at the other side. So it will do what? It will not be able to identify whether this bank is talking about the account or the river part, because it is only seeing from one side, or you can say it is looking at it independently. However, BERT represents bank using both its previous and the next context. I accessed the word bank is their account. So it will look at the previous words also and the next word also. And that is what the context based means. It is trying to make the meaning of that word based on the surrounding words. So starting from the very bottom of the deep neural network, making it deeply bidirectional. So whenever that neural network is created, to identify the connections or to create the connections between the words and the statements, it will look at from both the side and it will be on the basis of the context based. When I talk about the bidirectional, right? So bidirectional is always context based. That is why bidirectional is used. Unidirectional can be context free also, context based also, but most of the time unidirectional is context free. So when you look at this unidirectional contextual model, it is basically context free part we are talking, right? So it is looking at the word bank either with one side. If it is looking at the context, it is looking only on the one side, or it is looking at one word independent. Both things can happen. Now, so this was the idea about why this bi-directional approach is important. Because to understand a word, you need to look at the previous also and the next also. Understood? Context free, you see, context free means what? If suppose bank account is written and bank of the river. In this both statement, the word bank is coming. What is context free? Context free is saying that you don't look at the surrounding word. You just look at the word bank and say, what does that mean? Correct. So if you look at only one word, that is called context free. Understand in a simple way, not to get confused. Don't look at this further thing. Just remember context free means what? You look at the word bank independently, right? Independently means you're just focusing on that word. You're not focusing on the word around that. Correct? Independently. But when you talk about this, when you talk about what context based, right? Context based means what? Context based means that if you are trying to take a look at the word bank, you don't look at the word bank only. You look at what is behind that and what is after that. So it is not independent. In the context based, the meaning of a word is on the basis of the surrounding words also. But here the meaning of the word bank is independent. I can call it the riverside, I can call it the financial institution, both. I don't know at this point, but I can call it both. But in this case, in the context base, I will look first at the left side words and the right side word. I will look at the surrounding word. Then only I will say whether it is that financial institution or is it talking about the river side. That is the main difference between context free and context based. Yes, context based of course is better, right? Context based is of course better. You see, and word uses the context base because if you are trying to understand the meaning of something, is it not better that you are looking at the surrounding words? That will give you a better idea. So of course the context based is better, which is what the word uses. That is the idea. And the other things like RNN, LSTM, they use context free part also, and sometimes context based, but most of the time they use context free. And that is why they might not be able to understand the meaning of the word properly because they are not looking at the surrounding words. Correct? Now, so let's take a 5-minute break and then we will continue with this one. I'll explain the further part. I've given you this document. Just take a quick look at that. And if you have any question, I'll explain about that once. No, how can the training process be same for context free and context based? Context free and context based are trained in a different way. Context free things are trained on unidirectional approach, and context based are trained on bidirectional approach. Right? So in RNN, we were talking about that RNN, LSTM, we were doing this, that first we give one word and then one word is transferred to the next word, then it is transferred to the next word. We are going in a unidirectional approach. We are looking at each word in an independent manner, right? So sometime it can work well, but in most of the cases, it is not going to work well since it is not understanding the overall context. It is only looking at the data from one side. So it might not be very best. I'm not calling it that it will always be wrong. It is not always wrong. But in many of the cases, it can give us the wrong answer because it is not looking at the overall context of the statements. So their training process is different, of course. Okay, now, so it is written here. Moreover, BERT is based on transformer model architecture. transformer, whatever was there, attention mechanism was there and all of that. So instead of LSTMs, but is based on transformers, not LSTM. LSTM was the previous best thing before transformer came, right? So first RNN, then LSTM, then transformer, then BERT. So before BERT came, there were transformers, and before transformer, the previous best things were basically LSTMs, long short-term memory, right? So these were the things. So BERT is based upon transformers, not LSTM. So they have their attention mechanism. They have the concept of attention mechanism that they use. So what transformer do? A transformer works by performing a small, constant number of steps. In each step, it applies an attention mechanism to understand relationship between all words in a sentence, right? Regardless of their respective position. Wherever the words is, it does not matter. It will try to find out the relationship between each word. Which word is connected to which another word in the statement that we have written till now, it will try to find out that relationship. So suppose we have written, suppose let's take this is the statement, which is I arrived at the bank after crossing the river. Let us say I arrived at the bank after crossing the river. In this statement, let's say we have written till this much as of now. We have not written the further part after crossing the river. What transformers do, what the attention mechanism, there was a attention mechanism on which it is based upon. I have explained that also. Multi-headed attention, what does attention do? So attention is nothing but if you have written this much statement till now, I arrived at the bank. So it will try to find out which words in this much is connected to which other word. Like bank is related to arrived, I is related to banks, let's say. So which word till now is connected to which other word? It is able to find out. The attention mechanism is able to understand relationship between all words in a sentence, regardless of their respective position. So it does not matter the word is present where, after some word or at the end of the entire statement, does not matter. It will be able to find out their connections. So like the word river is connected to the bank. So it will be able to connect that with the attention mechanism, right? Because the whole concept of attention mechanism is to make that matrix where we have the similarity index between the words. We have a similarity index, we have a matrix I was discussing about. You can visit that video to understand it better. And using that, it can understand which words are more similar to which other word. And it can have that in mind. That is how transformers are able to perform better than the LSTMs, which can't do both. LSTMs cannot do what transformers can do. LSTMs cannot uh, find out a relationship between the entire statement because they cannot look at all the entire part of the statement. So suppose when you have written this much statement, LSTM, let's say, can only look at this much to this much. They have forgotten this much. So they won't be able to connect the word river with any of these statements from here to here because it has forgotten that. It has a shorter reference window that we have seen. Now, let's talk about mainly how does the BERT work. What is the main working of the BERT? Now we are going to understand that. So BERT relies on transformers. We have seen so many times. The word relies on transformer. The attention mechanism that learns contextual relationship between words in a text. When I talk about transformer, we are mainly looking at attention mechanism. That is the most powerful thing about the transformer. This concept of attention mechanism is the game changer part. Because of this only, today we are able to use GPTs. So in the world of NLP, the most powerful concept is attention mechanism. If the researchers would have not found this attention mechanism, we would not be using chat GPTs and all of that today. Everything is dependent upon this one particular word, attention mechanism. The ability to connect words with another words in the entire given document. No matter how large the document is, It has an infinite reference window and it can make the connections between the words, because of which it can read 30-page document also, and it can understand the entire concept, whatever is the relationship between different statements, paragraphs. It can summarize that, it can question answer, it can tell us the sentiment of any particular statement if I pick. That all is possible because of infinite reference window, which is given by the attention mechanism. So BERT relies on transformer. A basic transformer consists of an encoder to read the input text and decoder to produce the prediction of the word. That's a basic transformer. But the transformer that is used in the real world, that has 6 encoders and 6 decoders. Right. So when we talk about transformers, we have two parts, decoder and encoder, but not one. We have 6 encoders, 6 decoder overall to understand the meaning of that. Now, since BERT's goal is to generate a language representation model, it only needs the encoder part, right? So BERT is what? BERT is trying to create a language representation model, language model. It is not trying to predict anything that frequently. So when you give a data to BERT, when you give a training data to BERT, so BERT says that I only require the encoder part. I don't need the decoder part because BERT is not trying to do the prediction as of now. BERT is only trying to learn the data and create a language model. So the predictions or the question answerings and all of that will be done later. So for now, it will be only using encoder for making a language representation, language model. And this encoder itself will be able to answer if required in the further case. If you go to BERT and ask something, tell me the answer of this. So this encoder itself will be able to tell the answer. There is no need of decoder in this case. Correct. So BERT is saying that I only use multiple encoders. I don't use decoders because I am not trying to predict the answer directly. I am trying to first understand the language. I am trying to learn the data. So it requires only the encoder part. Transformers required encoder, decoder both, 6 encoder, 6 decoder. But BERT is saying that I require encoder only. And based on the encoder only, I will be able to make the language representation, and then how it will be working, that will be seen later. Correct? It is saying that. So the input to the BERT or input to the encoder for the BERT is a sequence of tokens. Sequence of tokens means what? Wherever we have a statement, so statement is broken down into words, and words are called tokens. Simple. Tokens means words. So the input to the BERT has multiple encoders. So input to the encoder for BERT is a sequence of tokens, which are first converted into vectors and then processed in the neural network. But before processing can start, BERT needs the input to be massaged and decorated with some extra metadata. So it is saying that before the processing can start, before the BERT can start learning the given statement, the input statement, it will add something more to the tokens. Correct? So it is saying that if you're giving me any statement, any input statement for me to learn that, so first what will be done? A sequence of the tokens will be created of this input. Means your word, the statements will be broken down into list of words. And then those list of words are converted into vectors. You know, the word embeddings that we do, it is converted into vectors. So after converting into vector, then input is given to BERT, and BERT says that, okay, you have given me the input statement, but I will not start learning that as of now. I need to add few more things into the statement. What are those? The first thing it adds to this input statement is called token embedding. What is token embedding? A CLS token is added to the input word token at the beginning of the first statement, and a separator token is inserted at the end of the each statement. What is it saying? CLS and SEP. See. So I have this statement here. The input statement is my dog is cute. One statement, and he likes playing. Statement 1 and statement 2. Two statements are there. So it is saying that when you have statement 1 and statement 2, if you're looking at that, so at the very start, it does not matter how many statements you are giving, 10 statement, 100 statement, 500 statement. At the start of the entire document, you have to add a word CLS. CLS represents the start of the statement. Wherever our document is starting, this CLS token is a representation of that. So it will be only added at the very start of the entire statement, entire data. And then the word SEP will be added to show where the first statement is ending and where the second is starting. And then where second is ending, third is starting. Right? So separator token will be added after every statement. Statement 1 ended, separator. Statement 2 ended, separator. Statement 3 ended, then separator. So separated will be added after every statement, but CLS token will be only added at the very start. So then you take the input, add these tokens, token embeddings. Then it looks like this. Then what do? You further do the token embedding. These are the words. So they have to be converted into vector part. That is what we call as token embedding. So CLS, my dog is cute, Sep, he likes playing. All of that will be converted into the vector form, the embedded form that we have seen. Once this is done, then we convert into, or then we do something called as segment embedding. After token embedding, after converting my actual tokens into vectors, we do one more thing, which is called segment encoding. What is segment encoding? Segment encoding is saying that we will write EA to all the tokens which are related to first part of the statement. So from here to here, this is basically my first statement. So it is writing EA to all of that to show that it is a statement. From here to here is one statement. Then you see from here it is EB. EB means from here to here it is another statement, EB. And then if there is another statement after that, so it will be writing EC, 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 EC like that to represent that is the next statement. So here, instead of EA, it can also use E1, 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 and then E2, 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 then E3, 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 E3. If more number of statements are there, it can use the E1, E2 approach also. After segment embedding, what it does the position embedding. Why position embedding is required? Because we are breaking down a statement into tokens. We have collection of tokens here. We have collection of words here, right? We are not giving the entire statement connected together. We have tokens. So a position embedding is very important to tell that the first word was CLS, then my dog is cute. Their positional embedding has to be also done. So overall, you see there are three embeddings which are being done. Take our words, connect into vector. These are token embedding. Then do the segment embedding plus add the position embedding. So when three types of embeddings are done, then your data is ready for given to the bird. Then this thing will be given to the bird after that, after adding these three embeddings. So token embedding, segment embedding, positional embedding. If the connecting words are used between two statements like and, does it use it? No. It will consider that as a single sentence. The separator is only used when you are using dot. Dot means one statement complete, next is starting. That is the separator. But in the cases of and, it will not be separate. Correct? And apart from this dot, what other things will be considered as separator? Comma. If you are using comma, that is also considered as separator. That before the comma, this is one part. After the comma, this is one part. Then after the dot, it is one part. So whenever you see these symbols, the dot, comma, these kind of thing, that is considered as the separate, not the word and like that. Yes, other delimiters also, but you see what you would be using, colon you would be using or semicolon you would be using. All of these things are considered as separator mainly. All of that. So whatever you use, dot, you use this, you use, or colon, semicolon, these are all basically considered as your separators. That's the point. Why segment encoding is done? Segment encoding is done to tell from where to where is my first statement. Suppose you have given this. See, take a look at this example. Suppose you are giving this much to bird to understand that. So you have to tell from here to here is one statement, and then from here to here is another statement. You have to tell that, right? So a segment indicating sentence A or sentence B is added to the token. This allows the encoder to distinguish between tokens. Two statements are there. So you are saying that add a CLS here, then add a SEP here, SEP, because you are separating it at this point. Then add another separator here after the end of the final statement. This is what we are saying, that you need to do segment encoding to tell from where to where your first statement is, and then from where to where your second statement is, from where to where your third statement is, from where to where your fourth statement is. That is what this segment embedding is doing. If while entering statement no punctuations mark is entered, then it will be looking at the entire thing. Right? Then in that case, it will be looking at the entire thing. But whatever documents are there, always there are punctuations. You won't see any document as such where no kind of punctuations are there. So whatever PDFs exist, articles exist on the internet, or a Wikipedia page it is trying to read, there everywhere some sort of punctuation will be there. If it is not there, then that document will not be understood very properly, because there is no separating point in that. So it will try to read the entire paragraph as one thing. It won't be able to separate that. Correct? No, we are not talking about users. This is all talking about the learning part. We are not talking about what user is giving. This is all about learning. Everything we are talking about till now is learning. How the bird is learning something, this is only we are talking. So when the users enter something, when the users give, in that case, when dot is there, dot is not there, it will not matter. It will be able to predict that, it will be able to understand that very properly. No matter what you're giving, how you're giving that. Because once in the learning phase, it has understood the context or how does a sentence structure is formed. When it has learned that, it won't matter what you give in the final thing. When you're asking something from the bird, it won't matter there. Correct? That is it. We are all talking about for the learning part for now. How does the bird learn something? When a statement is given to that, when it has to learn the context of the statement, it is talking about that. Essentially, if a statement contains, for example, Chennai, Tamil Nadu in this case, does not donate the end of the statement, right? Yes, see, that's a good question. If suppose it is written Chennai, Tamil Nadu, right? Tamil Nadu. So what will it do? Sorry, Tamil Nadu. So they both are same thing, right? They are connected. They must be connected together. They should not be treated as two different statements. For that part, what will your in this bird do? Bird will first think that they are separated, right? But bird has multiple encoders. There are 12 encoders or 24 encoders. There are multiple encoders. So bird will try to see a statement with multiple perspectives, different perspectives. So it will see that if I separate the statement from here on the basis of this, that whatever is before that is one statement, whatever is after that one statement, does it make sense? Right? There are multiple encoders specifically for this reason, that is it making sense to split the token from here, or should I split it from the next full stop or comma which is mentioned? It will do that. That is why you see there is not one encoder, but there are 12 encoders. And I was saying that also in the normal transformer also there are 6 encoders, which are all understanding the statement from a different perspective. One is looking at the statement meaning of that, one is looking at the syntax of that, one is looking at the grammar of that, one is looking at the position of that. So when multiple encoders are used, the benefit of these encoders is that it will be able to identify whether this separator is a good one for separating that or not. So it will not be treated as the sep by the bird. So in the start, when the first encoder sees that, it might think of it as a separator. But when it goes to multiple of these encoders, so finally the bird will think that no, this is not the separator token. After that, whatever is coming is a separator. That is what the advantage of the BERT is. Because of multiple encoders, it will be able to very smartly identify whether this should be a separator or not. Correct? That is the idea. So it is not, in this case, it will not be treating that as a separator token. It will be treating as overall the part of one statement. Now, essentially, the transformer stacks a layer that maps sequences to sequences. You see, essentially, the transformer stacks a layer that maps sequences to sequences. So the output is also a sequence of vector with one-to-one corresponding between input and output token with the same index. What is this part saying here? So this part is saying overall that if I have an input statement, right? If I have an input statement, so whatever final thing should be coming out, whatever final thing should be coming out of each word. You see, first input statement is broken down into tokens. Correct? What is the first thing? Input is broken down into tokens, multiple tokens. Then CLS is added at the start, and then separator is added at the end of each statement. So input is there, your tokens are there, which are broken down from a statement. Your tokens are there, and after those tokens, the word CLS is there, correct? Which is added at the start. CLS means the starting of the sentence, correct? It is saying starting of the sentence. It is to represent the start of the sentence. So CLS is there, then your tokens are there, then separator. It is saying that first statement ended here, then next statement started, next statement ended here. You have your tokens, then you are doing token embedding. You are converting these words into vectors. Then you are mentioning segment encoding, E1, E2, E3, like that. This EA, what are you seeing here, is saying that from here to here is one statement. These are all the tokens for first statement. And then from EB, whatever EB is mentioned, that is the statement for, right? That is the statement for the second one. These are the statement for the second one. And then positional encoding you do. Then that the first E0 was there, E1 was there, E2 was there, E3 was there, E4 was there. That is the thing. So this statement overall here is saying that it should understand the output that is coming out from here. It should be in the same manner. If the first word was CLS, after that these three encoding, whatever first thing should be there, that should be representing CLS. Then when the second part comes out, this embedded vector that comes out, this embedded vector should be for mine. Then this embedded vector should be for the dog. This embedded vector should be for is. When I say this embedded, I am not referring to E0. I'm referring to all three embeddings done together. Because on a word, three embeddings are being done, then you get the final answer. Final token, final embedded token. Then you have these three things combined together, then you have a final token. That is the thing. Right? It has considered that maybe it has broken down on the basis of whatever tokenization technique was used. On the basis of that, it might have thought of it as different. Correct. But the thing is, to understand the meaning of a word, ing is not required. You can say play. Play means what? Play. So ing is not playing here, is not changing anything. The word play is also same, and the word playing is also overall same. So it is saying that using the base word, I will be able to understand the context, and ing I will add later to say that, okay, this is done currently. Ing means we are currently playing. So it is done added as a extra context. ing part. So that depends upon how the tokenization was doing. What was the tokenization concept used in the previous overall the BERT? On the basis of that tokenization, it is separating. Now, so now the BERT uses these two things. Whenever we talk about the BERT does not try to predict the next word in a sentence. The BERT training make use of the following two strategies. Right? In the earlier, just after a few minutes, we have seen that BERT is not trying to predict the next word in a sentence. It is trying to predict the next word on the basis of the surrounding. Two ways it is looking at the data, then it is trying to predict the next word. So it is doing the prediction of the next word, but not unidirectionally, not by going from one side, but from the two sides at the same time. And how it is doing that? So it is saying that training makes use of the following two strategies. The first one is called masked language model. Understand this. These are the two main components of the BERT. How BERT learns something. This is what these two main topics are. Masked language model and next sentence prediction. On the basis of these two things done together, the training of the BERT is done. Let's see, then I'll take your questions. In the masked LM, I have given you idea about this just few minutes ago, but let's understand in detail with example. So BERT says that to understand the meaning of a statement, I will do these two things. And when I combine these two concepts together, then I can learn anything much better. How? Let's see. So the idea here is simple. Randomly mask out 15% of the words in the input, replacing them with the masked token. It is saying that whatever statement you are taking, 15% of the statement, randomly any 15% of the statement, you mask it. Mask means what? Hide it. And then tell the BERT to predict this 15% mask. 15% of the entire statement could be 3-word, 4-word, 5-word on the basis of the entire statement. Then it is saying that try to predict that. Now, run the entire sequence through the BERT attention based encoder and then predict only the masked word. Predict only the masked word based on the context provided by the other non-masked word in the sentence. So BERT, we are telling to the BERT that you have to predict the masked word. You want to learn how does a statement work? How is a statement created? You want to learn that, right? So it is saying that for teaching the BERT how a statement look like, the grammar of it, the structure of it, how a statement look like, we will do an exercise. The exercise is, the mask LM says that we will do an exercise where I will mask some word, 15% of the word of a statement, randomly any 15%. We look at the previous words and the surrounding words, left and right side, to be able to predict these 15% of that. Now, this is what it will do. However, if I teach the BERT using this approach, what is the problem going to happen? If I teach the BERT using this approach always, there is a problem with this naive masking approach that the model only tries to predict when the mask token is present in the input. Correct. See here, what will happen with the with this approach? What will be the problem with this approach? This problem is saying that we have to give a training data. All of you understand this. This is the final thing we need to talk about. You are taking a training data, you are giving to BERT. And BERT has to learn the training data. How a statement look like, how does a paragraph look like, how the sentence structure look like. It has to learn those things, the BERT. So BERT says that, okay, give me a statement. I will learn it. So suppose you have given this statement to BERT. How BERT will learn that? So BERT will say that I will challenge myself to learn it. I will not just look at it directly and say that, okay, I remember that. I will challenge myself to be able to be sure that am I actually understanding the statement or am I just looking at it? Correct. So challenge is BERT uses one tool inside of that. Masked LM is a tool which is used inside the BERT. which creates a challenge for the bird. The challenge is the mask LM says that, okay, I'll take a statement and mask out any 15% of the words. Mask out any 15% of the word randomly and then tell the bird, can you predict what word should be here on the basis of the previous words and on the basis of the next words? Can you predict what should be here? Bird will try to predict that. Then it will do the same thing for other statements also. So if you're giving, let's say, 10 billion statements, so same process will be done for 10 billion statements, same process. Every statement will be taken, some part of that will be masked, and it will try to predict that. By predicting it, it will see whether its answer is correct or not. If it is wrong, it will try to correct itself. Right? It will do the self-learning using the neural network. It will try to form the separate connections if it is wrong. If it is right, then it will let that connection be as it is. But now the problem is, what is the problem because of this? So during the training process, the training of the bird was done in such a way that every sentence was masked. Right? Every sentence was masked somewhere. Then the bird was looking at that and then predicting that. But in the real world, suppose in the real world, I now have to use bird to ask a question. So it is saying that the problem is when you ask an input question in the real world, you have to also give a mask token. Now we cannot give a mask token like it was done in this case. We can't say that who is the president of United States and mask something in middle. We can't do that. We are not capable of creating the mask token. Now it is saying that Bert is saying that I don't know. When you give the entire statement, I have not been trained on that basis. Whenever I was given any training statement, something was masked. So you also have to give me a statement where something is masked. But we cannot do that. So to deal with this issue, right? To deal with this issue, what we do, in 80% of the cases, you see that in 80% of the time, here the word time is missing here, 80% of the time, tokens are actually replaced with the mask. It is saying that 80% of the time, what we do, the sentences which are there, they are masked. Let's suppose 100 statements are there, 80 statement will be masked actually. Then 10% of the statement will be such that they will not be masked, but replaced with random words. At the place of actual word, we will put another word, but masking will not be done. And then 10% of the time, the remaining 10 sentences which are there, we won't do anything in that. So what we are saying, if I suppose have 100 statement I'm giving to bird, so from this 100 statement, which is being given to bird, 80% of those statements or 80 out of these 100 statement will be replaced with the masking, right? They will be masking in 80% of the statement. Then 10% of the statement, there will be no masking. But what will be done? The actual word, some actual word will be replaced by random words, which don't have any meaning in that. Replaced, which makes the statement incorrect. Then 10% of the time, the tokens are left unchanged. Now, when the variations are given here, when the three type of variations are given here, then your bird, which is trained, it will be able to understand that, okay, I can work on all the three cases. If the mask input is given, then also I can work. If wrong, if something is wrong written, I can also correct that. And if a question is asked as it is, I can then answer that further. Here, I don't have to complete anything. I have to look at the answer and then I have to answer something. I have to look at the question. So now it is understanding three versions of state. One is a masked one, which is helping it to learn the structures of the statement. Then incorrect words, which is saying that if these incorrect words are there, they don't make any meaning. You need to learn to correct them. And then some of them are left unchanged as it is, because some of the statement it has to see to learn how a statement look like. So three different challenges are there. And once it has been trained on these three different challenges, then when any input is asked, any question you ask it, it will be able to answer that correctly. It will not say to the user that you need to give me mask kind of input. It will not say to us. Now, after mask LM, mask like this, what was this? Mask language model, I guess. Hmm. Right. Now see, the next item which BERT uses. BERT uses two things. One is mask LM for challenging it to learn. Second thing is next sentence prediction. This is the next challenge or one more tool which is used inside of BERT, which is helping the BERT to learn. What is next sentence prediction? Next sentence prediction is a thing which says that in order to understand relationship between two sentences, BERT training process also uses next sentence prediction. To make it better, to make the training of the BERT better, to be able to understand the statements, connection between the statements much better, it also goes through one process called as next sentence prediction. It is also given one more task, which is next sentence prediction. In the mask LM, what we were doing, we were masking a part of the statement and we were telling it to predict that. That was one challenge which was done in mask LM. What we're doing in next sentence prediction is saying that a pre-trained model with this kind of understanding is relevant for tasks like question answering. During the training, the model gets an input pair of statement and it learns to predict if the second statement is the next statement in the original text as well. See, what happens in next sentence prediction, you must have understood, but it is saying that during the training of the BERT model, the model gets input as a pair of statements. The model will not be given input as one statement, it will give it two statements or three statements or five statements. It will give pairs of statements. When it is given pairs of statement, it learns to predict if second sentence is the next sentence in the original text as well. Now it will say that, okay, one statement I'm giving, second statement I'm. Now BERT has to understand, does the second statement come after the first statement or is it a very different statement? And it should not be the second statement after the first statement. Right? What do I mean by that? You see, take a look at the example. So next sentence prediction is saying that two sentences are there. The man went to the store and he bought a gallon of milk. Right? Here the mask word is the and the word to. The man went to the store and he bought a gallon of milk. Right? There is a dot here, which is representing as a separator. One statement, dot, he bought a gallon of milk. So the label, what the next sentence prediction will do, it will say that yes, second statement is next according to the first one. Second statement is actually the next of the first one. Right? Now, then when we are looking at the next question, the next sentence, the man goes to the store. Right? The man goes to the store. The mask word here is goes or went. Sorry. Here was the word went, which is masked here. The man went to the store. Then second statement is penguins are flightless bird. Right? Penguins are flightless bird. So are these two statements connected? Is the second statement the next of the first one? Not. It is saying not next. So second statement is not the next of the first. What it is trying to understand? It is trying to understand that after the first statement, what next statement should be created. If it has to do the text generation, it is learning that which is the next word which should be present after that. And from where it will learn all of those things? Training data. In the training data, there will be statements from which we are breaking it down and giving it to predict. If it is doing wrong prediction, it will go to the training data, match it. Have I predicted correctly? If it has predicted correctly, okay, it will learn that. If it has predicted incorrectly, it will try to correct itself. So everything is based upon the training data. There is a training data where it is mentioned there is a statement. The man went to the store, he bought a gallon of milk. That complete sentence is given in the training data, but that is broken down into two statements, and your sentence prediction, NSP, next sentence prediction. This tool is trying to understand whether the next statement is actually the next of the first one or not, on the basis of its understanding. On the basis of the context, it is trying to understand. On that basis, it has to understand whether the next statement look like the next of the first one or not. So by combining these two things, the concept of masked LM and concept of NSP, next sentence prediction, masked LM and next sentence prediction, when you combine these two things, these are the two tools which are present inside BERT. And because of these two tools present inside of that BERT can learn the things better. BERT can learn the language better, sentence structure better, meaning better, context better because of these two things. Because you're training it to do two things. You're training it to predict the middle word also, mask word also, and you're training it to predict the next statement also. So it will be capable of question answering, text generation, or completing the statement. It will be ready for all of that since you have these two things inside BERT. But transformer does not have these kind of things. So transformer cannot be trained on a very large data and it will not be working that well. But since BERT has these two very brilliant tools inside of that, mask LM and NSP, so it will be able to understand that. It is saying that not next. See, I'm saying here, that is what I was saying you. There is a training data. See, there is a training document. In this training document, these words are there, these statements are there in the complete form here. They are present in complete form in the training document, right? Now from the training document, these two statements were taken randomly by the NSP, next sentence prediction is a tool. It is saying that, okay, I go to the training document, pick up two statements randomly. So either they are together or they are very different statements from a document, right? I take that and then show it to my BERT, right? Show it to BERT. Now BERT has to think, does this look like two continuous statement or is it not two continuous statement? So it will predict something. Yes, the second statement is the next of the first. It will predict that. Then how does it know it has predicted correctly? Because correct answer is there in the training document. This complete thing, how they are connected, is the second statement after that. This is there in the document. It will, after prediction, it will go there and see the answer. Like you give the examination, right? When you go to examination, you answer a question in the examination, but you don't know whether it is correct or not. So you come back and take a look at the notebook. So in notebook, every answer is there. Same thing is happening. Your training book document is like that notebook where answers are there. You are going to the examination. This is the examination. And what is your answer? Your answer is this. So what is BERT doing? BERT is making an answer on the basis of what they have understood. Whatever they know, whatever context they have understood for now. On the basis of that, they will now do this, predict this. Now, have they predicted it correctly? They will go and match it. And they will see, yes, my prediction is correct. Okay, this is good. It has learned the pattern here. Second, one more training. In this training, two statements are there, but they are not connected. It is predicting not next. Is it correct? Then it will go back and match it. Have I predicted it correctly? If it has predicted it correctly, then it is good. Otherwise, it will try to correct itself. Suppose it has written it is next. That is a wrong answer, right? It is a wrong answer. So that is the idea here. According to this, it will go and correct itself because this is not the next sentence in that. The idea which we are getting. No, prediction. See, we are not doing prediction. We are doing sentence connection. We are trying to connect the sentences. Does it look like the second statement is connected to the first one? Is it completing the first statement? Is it adding some extra detail to the first statement? So it is trying to do that, right? So on the basis of these two statements, okay, you are not understanding. So you watch the video, then you will get it. I think you have to watch from the first. I'm saying a very simple thing. I don't know what is the confusing part here. Very simple thing I'm saying. Two statements are there, both separate. And there is a labeling. There is a document where the entire statement is given. Both the statements are given. It is trying to say that is the second one next or not. It is trying to predict that. If it is correct, then it is okay. If it is not, if its prediction is wrong, then it will go here, match it, and see that no, my prediction is wrong. So it will try to correct itself. Right? The second statement is not connected. So that is why it is saying not next. Because the second statement is not the next of the first one. That is why its answer is not next. Now, so this is what the overall architecture of the BERT is. The main two part of the BERT is the mask element and the next sentence prediction. So whatever I have discussed before this part and this two part is the main idea of the BERT. If you understand this much, this is what the BERT is all about. So what main two things you need to understand? The BERT has these two components, next sentence prediction and then mask element. Remember that whenever you go to interview, if someone asks you BERT, you need to explain first few things about the BERT, which I've explained before. But you have to say that BERT has these two components. One is called mask element and one is called next sentence prediction. These two components, on the basis of these two components, it will try to learn or it will try to challenge itself to learn the sentence structure, the meaning, the context, everything. It will try to learn using these two components, which is present inside of the BERT. Yes, what is the question? Ask me. With this, our concept is complete. After that, there are few things mentioned. Architecture of the BERT. There are two type of BERT, BERT base and BERT large. BERT base has 12 layers, where it is saying that basically 12 layers means 12 encoders are there in BERT base. And one BERT large was created, which was larger than the base one. And it is, you can say, second version of the BERT, which has 24 layers. So there are two versions of the BERT. One is BERT base and BERT large. That is the thing. Okay. Apart from that, whatever BERT working is till this much that we have seen. Yes, I'll share this also. I think this will be covered in the upcoming session, but if you want to take a look, you can take a look at that. Okay, for now, you all had to understand this working of the BERT. When I have shown you the example of Hugging Face, in the first few sessions that I've taken, I have explained how does Hugging Face work, right? Hugging Face models we were using and we were able to do the summarization, text generation, all of that. So when I was transferring the model from the Hugging Face, if you look at previous to previous, when we have done previous to previous, the first time when we started the Hugging Face concept and the Gen AI concept, when I started teaching, in the first two sessions, I have shown you some examples. In that example, we have used BERT. Okay, we have used BERT in that case. So BERT has already been shown to you, main part of the BERT. How do you use that? And the theoretical part of the BERT is shown here. Okay, now, yes, 1 minute. Let me give you the access to that. Just yes, now you will be able to access. Yes, so I hope the idea for today would be clear. I have shared this statement. I'll share this in the LMS also. But for now, you can bookmark it as of now. Just click on this statement. Click on this link. It will open up in your browser. Bookmark this so that you can keep that. And 1 minute. I have noted it down in a PDF format also. That also I'm sharing to you if you want to download that. So I hope overall idea about the BERT you must have understood. what was the transformer, and how it came down to the bird. What are the main tools inside of that? I hope this part should be clear. About tomorrow, I don't know. For me, it was the last session. And I think further, if there is any session, you'll get the mail regarding that for anything further. For now, whatever I have to take, whatever was given to me, I have covered that as of now. See, the bird that we use is the same way I have shown you in the first two sessions. Correct. In the first two sessions, when I was talking about the way we have imported the bird, you see, Hugging Face model. Go to the first two state classes that I've taught, and there I have shown you how to import these model from here onto your Google Colab, right? Google Colab. So in this case, the way the bird is used from here, like if I write here bird, you'll see bird base uncased, bird base NER, bird base multilingual cased, legal bird base uncased, bird base cased. These are different versions of bird. So uh, we have talked about this. We have seen how to use that for our task for text summarization, question and answer. I've shown you this the way you can use this bird. You can go to any of the bird, you can copy this, and you can use it as it is. You don't need to write the bird from the scratch as of now. When you go to company, then you will be required, you may be required to write it from the scratch. Then you can learn that. But for now, the way we have to use bird, I have shown that to you in the first two sessions. You have to go and you have to search. If you suppose want to use bird, so you search for that and you can copy this and you can use as the LLM we were talking about. Okay, so go to the first two statement when I talked about the Hugging Face introduction part. You'll understand, you will see bird I must have used in those examples. And that will give you an idea. You don't need to create the bird from the scratch. Bird from the scratch is created when we have to do fine tuning. Fine tuning as a fresher, you don't have to know about for now. Okay, right. Fine tuning is done on a larger data. So when you go to the company, if the company requires the fine tuning, you can do in that case. Okay. Okay. Yes, you can download the file from here itself. Just a minute.